Hey guys, this is our first time looking at exponential growth and decay. So with these I'm going to do one question per video because they can get quite long, and I also don't know how many I can track down. So this one is off of the AQA specimen paper 2 of the new A-level, which you can get from their website. So for this one then, David has been investigating the population of rabbits on an island over a 3-year period. Exciting stuff. Based on the information he has collected, he has decided to model the population with the formula R equals 50e to the 0.5 t, where t is the time in years after the 1st of January 2016. Okay, so it's worth noting here we are dealing with exponential growth. How do I know that? Because we have a positive power of e. So positive powers grow, negative powers decay. So part A here, or part 1 part A, is a very typical way to start these questions. So it's asking us, using David's model, state the population of rabbits on the 1st of January 2016. So remember, t is the time in years that have passed since the 1st of January 2016. On the 1st of January 2016, 0 years have passed. So basically we're substituting in t equals 0. So 50e to the 0.5 t when t equals 0 is going to give us 50 times e to the power of 0. Any number to the power of 0 is 1. So we've got 50 times 1. So our answer is 50. Very, very common way to start these questions. Okay, now part 2 wants us to predict the population of rabbits on the 1st of January 2021. So what we need to know here is how many years have passed since 2016, which is 5. So all we're doing is substituting in t equals 5. So we're working out 50 e to the 0.5 t when t equals 5. So we will get r equals 50 e to the 2.5, which gives us 609.12 blah blah blah. But remember here, we are modelling a population of rabbits. We don't want decimal parts for a rabbit, so we're going to round that down to 609. Good times. Nothing too bad so far. Okay, for part 2, slightly trickier maybe. So we want to use David's model to find the value of t when r is 150, correct to 3 significant figures. So remember we've got our formula, r is 50 e to the 0.5 t. Now we're setting r equal to 150. So we are using 150 equals 50 e to the 0.5 t. So the thing that we want is in the power, so we're going to need to use logs. Before we do that though, simplify as much as possible. So we can divide both sides by 50. So if we do that, we get 3 equals e to the 0.5 t. Okay, so now we've got a purely exponential term on the right, so we can now take the natural log of both sides. So we will get log 3 equals, now remember, taking the natural log of an exponential or of the exponential cancels out the exponential. So we're going to get log 3 is 0.5 t. Now we're almost there, we just need to cancel out this 0.5. So to do that, we're going to multiply both sides by 2. So we will get 2 log 3 equals t. Then we can write 2 log 3 using the laws of logs as log 9. So we get log 9 is equal to t. So now it's calculated time, work in log 9, and we get t equals 2.197 blah blah blah. Now we want this to 3 significant figures. So the third sig fig is the 9. Now that's got a 7 after it, so effectively the 9 rounds up to 10. So we actually get t equals 2.20 to 3 sig figs. Okay, and then we're asked to give a reason of why David's model may be inappropriate. So the one that struck out to me is that he only took data over 3 years. That's quite a short period of time to be modelling population growth. Other things are some unexpected factors may affect the population, like predators, disease, natural disasters. There's no cap on the population growth, so the way it's going, theoretically, his model can shoot off to infinity. Obviously, there can't be an infinite number of rabbits. They would get to a point where they are overpopulated and then they would start dying off. So he hasn't accounted for that. Anything like that would be a valid reason. Okay, a bit more problem solving now for the final part. So on the same island, C here models the number of crickets, the population of crickets. So we've got C equals 1000 e to the 0.1 t. We want to use both models here to work out the year during which the population of rabbits first exceeds the population of crickets. How are we going to do that then? Well, if the rabbits are growing quicker, which they are, they have an e to the power of 0.5 t, the crickets only have e to the 0.1 t. So the rabbits are growing quicker. So what we can do is find the value of t for when the populations are both equal. Now we know when they are equal, because the rabbits are growing faster, they're then going to take over pretty quickly. So let's do that. Let's set 1000 e to the 0.1 t equal to 50 e to the 0.5 t. Okay, now we want to solve that for t. So we're going to need logs, but first of all let's simplify as much as we can. So divide through by 50. So we would get 20 e to the 0.1 t is equal to e to the 0.5 t. both exponentials are in terms of t. So we can actually divide both sides here by e to the 0.1t. So if we do that, we get 20 is equal to e to the 0.5t divided by e to the 0.1t. Now, by the rules of indices, we then get 20 is equal to e to the 0.4t. So now we need to get the t term out of the exponential. So take a log of both sides. So we get ln 20 is 0.4t. Divide by 0.4, we get t is log 20 divided by 0.4, which is going to give us 7.49. So 7.49 years after the 1st of January 2016, the populations are equal. And then again, because we know the rabbits are growing faster, they're then going to take over. So what year is it? 7.49 years after 2016. It's 2023. So 2023 is the year that we would expect the population of rabbits to first exceed the population of crickets. Good times. Big question. We're done. See you in the next one.